Welcome to the EPG Pathashala, the lecture series in computer science for the postgraduate program. And this is the compiler design course where we are on module 32, where we will be discussing about the code generation algorithm using the directed acyclic graph. And the next thing which we will talk about today's module is the dynamic programming approach to code generation. So, the objectives of this module are to understand the code generation algorithm from a DAG and to learn the dynamic programming approach to code generation, where we will be looking at a contiguous piece of execution in a bottom up fashion, where dynamic programming strategy is adopted for computing the cost and choosing the appropriate instruction. So, code generation from DAG. So, the previous modules we have talked about constructing a DAG and how this DAG can be labeled using which is nothing but assigning it the label as the registers required to compute a particular interior node. And then we have also looked at how to reorder the DAG so that the instructions can be done in a faster, can be scheduled such that the total cost of instructions is going to be less. And in addition also we have seen that if you reorder the code, it also avoids the spilling of registers where we have to swap to and from the registers. So, that is also avoided if you try to reorder the statements of a particular basic block. Now, here this algorithm uses a recursive procedure on a labeled DAG and it considers code generation based on the labels assigned to the nodes. So, this is the basis for branching and choosing the appropriate instruction. So, here we are going to use a stack of registers which is called as R stack, and that R stack will have registers, number of registers required. Now, we already know that the root of the DAG basically contains how many registers are required to compute that particular root node. So, which essentially is nothing but the total number of registers required to compute a particular basic block. So, that will be pushed into a stack which is called as the R stack, which is nothing but the register stack, and you will also have a memory stack which is going to have just memory locations M0, M1, etc. So, that if in the case of there is a failure on the registers, it will go to basically a memory based instruction. So, here the leaves this algorithm, it leaves the registers on R stack in the same order it found them. It leaves the registers on the R stack in the same order it has basically found them. So, the function we are going to use here is called as a swap, where it will look at the R stack content and then it interchange the top two registers on the stack. Okay. So, this is called when we want to swap the two registers which is available on the stack, that is one more function. Other than this function, the push and pop function which is typically for a stack is also going to be used. So, we are going to have 5 cases here. Case 0, that is if n is a leaf node and it is the leftmost child of its parent. So, that is one situation where we generate just a simple load instruction, where we will simply move the particular register into particular variable into a register. So, that is the first simple case, case 0. And case 1 will be where we have a subtree of the form for which we generate code to evaluate n1 into a register R, which is available in the top of the R stack, and followed by the instruction operator name R. So, this is the next case where we will look at generating the second statement corresponding to the simple code generators function, where you have opcode and then some the name of the variable followed by the register. That register is available in the top of R stack. And the third case is case 2, where you have a subtree of the form where n1 can be evaluated without stores, but n2 is harder to evaluate than n1 as it requires more registers. So, here n1 is the left child of a particular interior node and n2 is the right child of the particular interior node. And for this case we swap the top two registers on R stack and then evaluate n2 into R, okay, and then we remove R from R stack and evaluate n1 into at the top of the R stack. So, here what we do is if n2 label is more than n1's label, n2 has to be computed first. Since typically the top of the stack register is used by N1, okay. So we have to swap the register such that these top but next, that register can be used for computing the value of the node N2, okay. So using that we generate, and then the instruction is basically pushed onto, and then finally you do a operator r comma s, so that it can basically be evaluated and the result could be available in the top of the stack s. So another call to swap leaves r stacks as it is when this call is a call of gen code basically begins. The fourth case, which is nothing but case 3, it is similar to case 2, but here the left subtree is harder than the right subtree. But here what happens is, since left subtree has to be computed first, we don't do a swap of r stack, okay. We start evaluating directly the the left subtree before evaluating the right subtree. And the last case is, it occurs when both subtrees requires r or more registers to evaluate without any store. That is, here we already know how many registers are required to compute a particular DAG. Now supposing the number of registers available in the R stack is less than the total number of registers required by the particular basic block. In that case we have to go for case 4, where we will be using a memory based instruction to issue, and that will be computed using the memory itself rather than using registers. So here to support this case, what we do is we have to have a stack of memory, where again it is going to be a stack of memory. So T0, T1, T2 etc. will be available there. So this is the last case. Now the algorithm here is very simple, where this is case 0. So case 0, what are we looking at? We are looking at simply issuing a move command, where n is a left leaf representing an operand name and n is the leftmost child of its parent, okay. It is a leaf node and it should be the leftmost leaf of its parent. So in that case I simply say issue a command, move the variable name onto the register available in the top of the stack, top of R stack. So supposing if I have the variable name as A and R0 is my top of the stack register, I will issue a command here, move A comma R0. Now this is the terminating case, and the other case will be if n is an interior node whose operator is OP and whose left child is N1 and right child is N2. So this is the scenario. In that case what we do, we have to look at case 1, 2 or 3 or 4 basically. So what will I do? I will check whether if N1 is heavier or N2 is heavier. If N1 is heavier, I will call case 3. If N2 is heavier, I will call case 2, and if I am not able to match the number of registers, I have to call case 4. Now case 1 will be called on one particular situation where label of N2 is equal to 0. That is, this is going to be a special case where I will be looking at the last but the last level of a particular DAG. So label of N2 means what? We already assigned the labels to N1 and N2 such that if N1 is a left child, you assign, and if it is a leaf, you assign a value of 1, and if N2 is a right child, you assign a value as 0 if it is a leaf node. So that resulted in computing an interior node, which is the last but one interior node, can be computed with just one register. So that is the reason here we are going on to case label of N2. Now before looking at whether it is left heavy or right heavy, we have to check whether am I computing the last but one level of my DAG tree, okay. So that is what we are trying to look at here. So if label of N2 equal to 0, then let the name be the operand be represented by N2, and so then you have to call gen code of N1. So in that case what you do is you have to look at gen code of N1, meaning that call it with the left child, call this algorithm recursively with the left child. So in that case again it will come to this scenario, because typically that case it will be case 0, where you will be having a left leaf and then you have to issue this command, and then followed by that you have to issue this operator command. So when I say label of N2 is equal to 0, I am talking about a situation where it is nothing but the interior node happens to be the last but one level of the DAG. So that case what will I do? I have to compute the left child by moving that variable into a register, okay, and then that is what is done by this particular statement out here, the gen code of N1. This will typically end up with this, or it can basically be called with something else also, but ultimately speaking, this is what is going to basically happen. It can basically follow under case 2 or 3, but to be on a very simpler note, it will be the last but one level if that is going to be our situation. So it will basically call this first, which will be essentially this instruction of move command, and then followed by then I have to do an op. Okay, so that is also done. So the next one is case 2. In case 2, what we do is we will check whether the label of n1 less than label of n2 less than label of, and label of n1 is less than r. Okay. So here label of n1 is less than label of n2 means I am talking about where n2 is heavier. So this is what we said as case 2. If n2 is heavier, and not only that, I will also check whether you have here less than r, is it going to be overshooting the number of registers. If that is the case, I will basically have call case 4. So I will do that. Okay, so in that case what I do, I swap r stack. So if I swap r stack, I have changed the position of the registers available in the stack as r0, r1, and then I do a gen code of n2. Okay, I'll call with the right subtree. Okay, that right subtree will go through any of these, and then I'll do what, I have to pop r stack. Okay, and then I have to push calling that as r. Okay, and then I have to call with gen code of n1 with whatever is available in the stack now. So that will and then I have to use a command operator r, which is the popped stack content dot top of r stack. So top of r stack will have the n1 evaluated, and this r has got n2 evaluated. So I will issue a command operator, which is the interior nodes label, with the n2 followed by n1. This is one more, and then I'll have to push this r stack back onto r back onto r stack, and then I have to now swap. Now swapping basically ensures that n1 which was computing is available in the top of the stack itself. So this is what it basically does. So you have to first swapping because n2 is heavier. So to compute n2 is typically computed at the, n1 is typically computed at the top of the register, and therefore I have to swap. And second thing is I have to compute n2 completely using the same gen code algorithm, and then I have to pop this register. Once I pop this register, I will call gen code with n1. I will then issue this particular command print, just operating on the interior node using the popped register and what is available in the top of the stack, and then I have to push this register back onto the stack. Now what happens, n2 will be, the computation of n2 will be available in the topmost register. I swap these two contents to ensure that the topmost register always contains what is to be evaluated by the left child of a particular interior node. Now case 3 is just the reverse of case 2, where I will call gen code of n1 first, I will pop, I'll call gen code of n. I need not swap here. That is the only difference between case 2 and case 3. So this is what we have done, and then I have to push. Anyway, I have popped one value, I have pushed. The swap alone is basically not available in case 3. Now case 4 is where the labels of the nodes n1 and n2, which is the left and right children of an interior node, that has labels greater than or equal to the total number of available registers. Then I have to basically call gen code of n2, and t is equal to pop of t stack. Now this t stack is nothing but temporary register area, where it's going to basically be a set of memory locations. And then I will do this move, I'll then call gen code of n1, I will push this stack back into r, and because gen code uses only the stack r register, r stack basically, and then I have to push this. So these things are operating both on memory as well as on the top of the r stack. So this is what is the algorithm. Now let us take at this particular example where we have got this is the already we have done labeling of this tree only earlier. So this is what it basically is available. So I have 1 0 1 0, this is 1 and a 1, and this is 1 2 and 3. So look at this, this gen code of A will result in case 0. Gen code of this node T1 will result in case 1 because right child's label is 0. Similarly, for evaluating T2, it will fall under case 1 because right child's label is 0, okay. And this interior node, okay, this interior node will have equal labels basically. So in that case I can evaluate either this or that first, so depending upon whichever has been done less than or equal to or less than. And similarly, to evaluate this particular node, the root node, N2 is heavier, so I have to do a swap and then basically call gen code of N2 first and then gen code of N1, and then I have to integrate them together to get the code of corresponding to the root node. Okay. So let us take this example. So I am going to call the input with gen code of T4. Okay. So I will have here corresponding to T4, I have two registers R1, R0. This is what I said, the left register, the left subtree has a label of 1, right subtree has a label of 2. Okay. So since right subtree is heavier, I have to use case 2 here. So case 2 means call gen code of T3, that is for the right child. In that case what happens, I have to swap the registers and then call gen code of N2. Okay. So I have swapped the registers and I have called gen code of T3. Now if you remember, T3 is here, okay, T3 has got same labels. So in that case it is going to be evaluating on the left child will be given priority, okay, left subtree will be given priority. So what happens is case 3, so I will call gen code of E, which is going to be case 0. So if it is case 0, I will simply issue a move command, okay, and then the control will get transferred back to T3. It has to continue at where it left, it is a recursive call. So in that case what happens is, I will pop the register. So I have popped R1, I have only R0. So gen code of T2, that is the interior node. So that case the interior node will have a left label as 1, right label as 0. So if the right label is 0, I have to simply call gen code of C, which is again case 0, and then this is the command for gen code of C, and then I have to call print add D comma R0, because that is how basically this case will terminate. So again it will fall under case 1. So case 1 will call the left child and then issue this command. So this will complete this particular situation, and then gen code of T2 will be subtract R0 comma R1. This is corresponding to this particular swap, gen code of E case, okay. This corresponds to gen code of E case. So where I did a subtract of R0 comma R1, I have to now push something back onto the register, okay, calling gen code of T1, and then I will call gen code of A here, again same thing, move A comma R0, print add B comma R0, okay. So R0 again is going to be case 0, this is case 1. So case 1 will basically have a move followed by an operand operator related call, and then I have to do a subtract R1 comma R0, subtract R1 comma R0, that is going to be your root. So the answer will be in R0, which will be the top of the register, okay, top of the R stack, register stack, R stack, okay. So this is what we have done. So where the labels of the code gen algorithm are used for generating the final code. Now multi-register operation, it supports only okay, the code gen which we have done so far supports only one register based operation, that is move A comma R0, add B comma R0, etc. If you have to support multiple registers, then the label algorithm has to be changed such a way that if you have the labels of L1 and L2 do not match, then you assign the interior label as 2, where you have one register for each of the left and right children respectively. Other case will be simply adding it by 1. If L1 is equal to L2, you assign increment the number of registers by 1 to compute the interior node, okay. So that is what is the next one, and I can also use some algebraic properties for DAG computation, where you can swap the left and right right nodes to effectively use a code generation algorithm to incorporate associative property or commutative property of algebraic laws. So one more thing is the common sub expression need not be recomputed, that can also be adopted here. Now so this is one approach to code generation. The next approach is called as a dynamic programming based approach to code generation, where the input will be again a directed acyclic graph only, Okay, the input will be a DAG, but the DAG will be labeled with the computation cost of a particular interior node. Now, we already know that for a particular DAG, how many registers are required to compute, okay, till the root. Now, supposing I want 2 registers to compute, okay. So, what we will do is we will compute the cost of computing an interior node, or rather every node. We will start from the leaf node. What is the cost of computing a particular interior node when there are no registers, when there are 1 register, when there is 2 registers, okay. So, we will compute it as when there are no registers, when there is 1 register, and when there are 2 registers. We will just check that and we will assign the cost there. Now, this cost computation is done on a dynamic programming strategy. That is, dynamic programming strategy means what? Given a choice, I will look at all possible combinations and I will adopt the one which has the least value. So, in this case, my overall aim is to reduce the instruction cost. So, what I would do is, I will check whether whichever is cheaper, I will use that cost as a basis for computing a particular interior node with that many number of registers, okay. And it is a bottom up fashion, it is a bottom up approach. Finally, the root will be also having a label which will have the corresponding cost for computing that interior, that node at a cost of at a cost with no registers, with 1 register, or with 2 registers. So, what happens is you have to compute bottom up for each node n of the expression tree T, an array C of cost in which the ith component C of I is the optimal cost of computing the subtree S rooted at n into a register, assuming I registers are available for the computation. So, this is what I have just now explained. I registers, how do we know? We know that because you already have labeled the tree, okay. Then you traverse the tree using the cost vector to determine which subtrees of T must be computed into memory, okay. So, this is the approach, and traverse each tree using the cost vectors and associated instructions to generate the final target code. The code for the subtrees computed into memory locations is generated first, okay. So, this is the 3-step procedure where you compute the cost first and then traverse the tree from bottom up fashion, use the instruction already known to you and then generate the instructions accordingly depending upon how many registers are going to give you the optimal cost, okay. The assumption here in this algorithm is only 2 registers are available. I mean, whatever example you are going to consider, we assume that you have only 2 registers, and these are my instructions. So, my instruction is not going to be now a move or a add, etc. My instruction is going to take the form as indicated here. So, Ri is equal to Mj, then which means that move the memory content into register Ri. Then I have Ri is equal to Ri operator Rj. So, what does it mean? It is something like adding Ri and Rj, and the result will be in Ri, okay. And then the next one will be Ri operator Mj, okay. So, now this is very careful, this has to be watched very carefully. Ri is in the left subtree and Mj is in the right subtree. So, if I have to compute this, result will be in Ri, okay. And then this is simply says Ri is equal to Rj, where I am just moving the contents of Rj into Ri also. This is just a register copy. And then this is the memory based copy where I will remove the register content into memory. So, this is mem copy, this is register copy, this is register copy, okay. So, Ri operator Rj means the left subtree could be in a register, right could also be in a register. I can operate that and then result will be in the left subtrees register, that is the condition. Second one here is Ri operator Mj. Now, I am assuming only that these instructions are available because the textbook Aho Sethi Ullman talks about only these instructions. You can also add additional instructions if required, okay. But for a understanding purpose, we are looking at only these instructions. And one more thing is all these instructions are assumed to have unit cost, okay. So, this will cost you 1 unit, Ri is equal to Ri operator Rj, that is also going to cost us only 1 unit. That is the basis for our example, okay. So, cost of computing a node which is in memory involves 0. So, if a variable is already in memory, then computing that particular node is going to cost us 0 for memory based instruction. And then we also assume that you have only unit cost for all these instructions. Now, let us look at this example. This is what we have computed, Okay, this is the final result. So let us see how we get this. So as you could see, I am having a vector here which has got 3 values. Now this 3 values correspond to cost of computing this node with no registers, with 1 register and with 2 registers. Okay. Now we will explain how this is being formulated. This DAG, this tree, expression tree is similar to what we have already done in the previous example also. The operators have basically been changed, which is okay. As of now we are looking at multiplication is also going to be costing me 1 unit, addition is also going to be costing me 1 unit according to this example which you have basically taken. So, but the tree structure is similar to what we know. So, therefore, this tree can be computed using 2 registers, that we already know. Now, let us look at this computation. So, cost of moving a variable, we are looking at the leaf nodes to start with. Cost of moving a variable with no registers is 0 because the variable is in the register itself. Okay. And then cost of moving a variable with 1 or 2 registers is 1 using the instruction Ri is equal to Mj. So, I can move Mj into Ri. So, whether I have 2 registers or 1 register, if I have to move the variable into a register, that is going to cost me only 1 unit. So, Ri is equal to Mj. So, cost of computing this particular node, the leaf node will be 0, 1, 1 because with 2 registers also I have to issue the same instruction only. With 1 register also I have to issue the same instruction only. Therefore, the cost of computing the interior node is going to be only 0, 1, 1. So, you can see that all these instructions are going to have 0, 1, 1. The next node is at 3, 2, 2. Okay, we will see how this is getting computed. Let us look at this last but one node. So, you have to find all possible cost and choose the one with the least cost. Okay. So, I have here 2 options, computing a particular node with no registers. Okay. So, what I should do is, but of course, I do not have a memory based instruction according to my instruction set. So, what I will do is, I will move to a register, compute it, okay, and then transfer the information back to my memory. Okay. So, the instruction would be, I can move Mj to Ri, I can do a Ri operator Mj, result is an Ri, move Ri back to Mj. So, this is the next option. So, this is going to cost me 3 units. Alternately, I can say Ri is equal to Mj, Rj is equal to Mi. So, I am going to get 2 variables into 2 registers Ri, Rj, and then I can say Ri is equal to Ri operator Rj, and I can say Mj is equal to Ri. This is going to cost us 1 unit. So, totally this will cost me 4 units, whereas this will cost me only 3 units. Okay. Since this is going to cost me only 3 units, I will choose that as my representation. So, I will use this. So, dynamic programming is used basically here where I have 2 possibilities. I will choose the one with the least value. So, using cost of computing the last but one level node with no registers will be 3. So, we had a 3, 2, 2. So, that is the 3 here. Okay. The next one is with 1 register. Okay. With 1 register will be exactly similar to this, but I am not moving this value back into the memory. Okay. That is the only thing I am trying to do here. So, this is the same thing. This is because it is already in memory only. So, I have to move it to register. I can then use Ri is equal to Ri operator Mj. Since I can use 1 register, I need not move this back to memory. Okay, that is going to cost me 2 units. On the other hand, I can, if I am going to use 2 registers, Ri is equal to Mj, Rj is equal to Mi, I am moving both into the register. I can use this, Ri will cost me 1 unit. So, Mj is equal to Ri, this is going to cost me 1. This is one more option where I can, it is going to cost me 4 units. So, I will compare 2 with 4. So, I will use only 1 register. So, this is going to be the cheaper one of the 2. The next one will be this one, where again I can, it is similar to the previous one only. I could use 2 registers, okay. I can free 1 register, but this is cheaper compared to using 2 registers. Therefore, that is also going to be only 2. So, this computation is also going to be 3, 2, 2. So that is why the next level also had a 3, 2, 2. So cost vector of the last but one level is 3, 2, 2. The next level will be, we had a 5, 5, 4, the root was actually 8, 8, and 7. So compute the left subtree with 2 registers available into register R0, compute the right subtree with 1 register available into register R1, and use the instruction add R0, R1 to compute the root. So this sequence has a cost 2 plus 5 plus 1. Okay, so that is why we have done here. This is similar to that only, and this sequence will also have a cost of 8. So with one register it is going to cost us 2 units, so 7 units means I can use that itself for my computation. Okay. So the first example here, the first instruction will be R0 is equal to C, then R1 is equal to D, then R1 is equal to R1 by E. So this node requires only one register, we have done that. Then its parent R0 is equal to R0 into R1. Now I want R0, but R1 could be reused. So R1 is equal to A, R1 is equal to R1 minus B, R1 is equal to R1 plus R0, which is the root computation. So this is going to be computing in this particular fashion, where I am going to use only 2 registers with a computation cost of totally, so as you can see 1, 2, 3, 4, 5, 6, 7. So we saw that the root had a 8, 8, 7 with 2 registers. So if you assume, we have assumed unit cost for this computation. So each, I have 7 instructions, all will basically is going to cost me 1 unit each, means I am going to have a cost of 7. So this is what was done with the dynamic programming approach. So where we kind of had multiple possibilities of computing cost, and then we chose the one with the least value. So on summarizing this module, we have looked at the DAG based code generation algorithm, where we looked at the labels which was assigned to all the nodes. The labels correspond to typically the number of registers required to compute a particular interior node. That was used as a basis to generate code. So where we had 5 cases to handle, and case 0 is the simplest of all, and it's happened to be the leftmost leaf node of a particular parent. And then case 1 was where it is the last but one level, and case 2 was a left heavy subtree, and case 3 was a case 2 was a right heavy subtree, and case 3 was a left heavy subtree, and case 4 is the labels of the interior nodes has a value greater than that of the number of registers available. So that was also discussed. And then after that we looked at the next alternate to code generation, which is nothing but a dynamic programming approach to code generation. So with that we conclude this module, and thank you.